Okay, so I think we can close the door on, per se, your activity yesterday. And that's how we learn, that the idea behind some of these problems like this one, okay, it's going to come out nice and even for you probably. And some of the problems that we do with finding the formula of a hydrate, those come out nice and even for you. And for those of us who were here for that activity, we see that it's more difficult than what you may think. And the process of whether it's a hydrate or whether it's an empirical formula or molecular formula, we all approach them in the same manner. So if you're tuning in from home or at a later time, we see this 300 gram sample that we're possibly placing in a mass spectrometer, or probably more likely than a gas chromatograph, probably your mass spectrometer. And I believe my interpretation of when you have that solution in there, a laser beam shoots through there, and the machine is calibrated to, as the refractions are shown through there, gives the different elements in their quantity. So everything added together should reflect your 300 gram sample. That might be something even like whether it's citric acid, or in this case, whatever this compound calculates to be. But the sample is found to contain 82.4624 grams of molybdenum, I believe is what you call element 42, 45.741 grams of chlorine, and then the rest is bromine. What is the empirical formula? Now, this is worded slightly different than your percentage problems that we've seen, okay? Because typically when you're given a percentage of that substance in a compound, it would all add up to 100. The concept is still the same. It's just that this unknown sample you may have weighed and it says 300 grams. So you still follow the same process. You do what with these two numbers? You would add them together and subtract it from 300. And then that would give you your amount of bromine. Okay. So is this one where we have someone come up here and teach the class?
I got it.
I think I got it today.
You want to volunteer for that?
Sure.
Okay, I just need to hit pause and we will tune in just a little while. Okay, so as you can see, we had a student that worked through this, and anytime you're looking for an empirical formula, all of these, we start with your grams, you're going to change them to moles. This number, as we said, you add those two together, gives you a certain number, and you subtract from 300. That's where that number comes from. Then notice these are all molar masses. It comes out to these numbers of moles, because you can't write molybdenum 0.86 and chlorine 1.29 and bromine at 2.15. So like what you had said, you find the smallest one. This one's the simplest because you divide it into itself. That's why there's one. Okay, 0.86 goes into here at 1.5, and then into here comes out as 2.5. So therefore you can't leave these as halves, so you double them, and that's why we get that answer. Yes, I believe you call it molybdenum, or else feel free to name that element. It's not that easy. For me, it's not. Maybe it is for you. Yes.
So say for like in this example, if the molecular formula mass was like 600,
Okay.
it'd just be 2. So would you just double?
Are you talking about this number?
Yeah. Like
That will not change anything.
No, like if you're trying to like find the molecular.
Well, okay. So, to answer your question, just a moment. We'll just hit pause for a moment. Okay. So the question is what about if this was a molecular formula problem? Well, what we would do differently is the only thing we would change is just this. Then we would have to say if the molar mass was 422.8. We'll just say 422 grams per mole. Okay, so then there's our question mark. So then notice what happens here is, well, I guess there wasn't a decimal there. We know that if we have a molar mass given a problem, so the molecular formula mass goes up on top, 422, and then what you calculated for your empirical formula mass, we know came out to be, well, whatever half that is. Divide by 2, 211. So let's see if that makes sense. Okay, so if we took 95.95, we add 35.45, and then we add 79.9, that gives us 211.3. So that's got to be right then, okay? Because this whole number ratio, even if you change this, you could put a 10,000 on here. It's still not going to change these numbers. It's still going to come out to this ratio here. Okay? So then what would happen is you wouldn't do anything with this afterwards. This is just your sample that you're starting with. You have to be given this number. That's why it goes on top. Whatever it is you calculate for this goes on the bottom. You divide that out. Oops. X equals 2. Which then means this whole thing has to be multiplied by 2. This number comes from adding those 3.
So you don't add it from the empirical formula?
That we just did.
But they're
Like the MO.
Oh, I see what you're saying, is you have to add 2 of those, 3 of those. Yep, that's what you have to put down there. Yep.
Wait, so that O equals 211?
No, that's if you had just one of those, one of each of those. So what that would mean is you'd have to go by this,
I get
95.95.
Yeah, that's what I got. I was 697.75.
Okay, 697. Okay, so that number goes down here, 697. So then this, if it was maybe 2,100 grams per mole, okay? What happens if we put 2,100 up there? What happens if you divide those two? You're going to get 3. That's right.
Then for your molecular formula, you just multiply all those, like what you have by 3.
Yes, then this is no longer 2, but rather 3. So then saying the ratio of this must be MO6, CL6, nope, 9, and then BR15. So this is your molecular formula. This, as we calculate, was your empirical formula. Okay.
Wait, so how did you, what was the first one that started off with like 422 and then 211? Like where?
I just looked at this instead of all of that. Yeah, I didn't calculate that correctly. Yes, because you have to find your empirical formula mass comes out, that's this number. So then what you would do is if you're writing these problems, you would say if you want this number to come out to 3, just multiply it. Well, that's pretty close to 700. So then 7 times 3 gives you 21. So, well, let's change this to 2,100 grams per mole. That's why it comes out to 3.
Would it always come out as a whole number?
It should, yes. It should. These are the ones that don't come out quite as a whole number. Okay? Anything else you would like to add?
Okay, so what's all gonna, empirical, molecular?
Yes.
Just those two? And not the hydrides or anything?
No, we said that earlier.
Said that, but I was
We
just-
said that, yep.
Percent composition.
We did that already.
Well, I didn't know if we were gonna do it again.
Okay? Not until your exam, because I think one of the things you're going to notice that as we keep progressing through this, naming compounds, that's not so bad. When you're adding the atomic masses, yes, you can make a mistake on those. Yes, that's true. Then we did your molar mass problems and percent compositions. Okay, we're familiar with those. Those aren't so bad. Then you jump into these types of problems, your empirical and molecular formulas. It's maybe a little more difficult. Okay? So then that's the material's getting harder as it should, because just like as you gentlemen progressed through the football season, once you got to the playoffs, did the opponents get more difficult?
Yeah.
Yes, as they should. Going through districts, or what would you say? Quarterfinals, semifinals. Yeah, you can say it all differently. Your regions, okay? First one, 3-0. The second time for sure was 3-0. And then you could say, then your semifinals or your round of 16 went to 3-0 as well. The competition, yeah, maybe.
Each of them was, like, I would say each game got harder.
Okay.
It's just we knew how to manage it. Like, I feel
Yep.
like the teams that we played have never been.
So that's all we have. So we will catch up to you next time. That's right.
the only time I